This is the solution to Chapter 8, Problem 5. The problem reads, a bead slides without friction around a loop-the-loop. The bead is released from a height h equals 3.50 r. A. What is its speed at point A? And B. How large is the normal force on it if its mass is 5 grams? We're given that the height is equal to 3.50 times the radius of the loop-the-loop, and the mass is equal to 5.00 grams. We're also given a diagram of what the problem looks like. For part A, in order to find the speed of the bead, we can use the formulas for kinetic energy and potential energy. The formula for kinetic energy is K equals 1/2 mv squared, and the formula for potential energy is U equals mgh. We can combine these two equations to say that the potential energy at the initial point plus the kinetic energy at the initial point is equal to the potential energy at the final point plus the kinetic energy at the final point. By plugging in the two equations for the potential energy and the kinetic energy, we can get the following equation. Note that the initial kinetic energy is equal to 0 because the bead is released from rest. Since mass is on both sides of the equation, we can cancel it out from the equation entirely. After that, we can plug in our initial height to be 3.50 r and our final height to be 2r, since it's at the top of the loop of radius r. Once we do this, we simply solve for v, and we get the answer to be v equals the square root of 3.00 times gravity times the radius. For part B, we can use the equation that the sum of all forces of F equals mass times velocity squared over radius. Because the bead is at the peak of the loop at point A, we know that the sum of all forces is equal to the normal force plus the mass times the gravity. Because we're solving for the normal force, we can move the mg over to the other side to single out the normal force. After that, we separate the mass from the rest of the right side of the equation, and then plug in the velocity that we found in part A. When all of this is done, we get a normal force of 2.00 times the mass times the gravity. After that, we simply plug in the mass and the gravity so that the normal force is equal to 2.00 times 5.00 times 10 to the negative third kilograms times 9.80 meters per second squared. Finally, multiplying all of that out gives us a normal force of 0.0980 newtons in the downward direction. And that's how you solve Chapter 8, Problem 5.